All right, we're good. Hi, everyone. My name is Bassam Tabbara. I am the CTO at Quantum, where we started this project called Rook, which I'm excited to tell you about today and walk you through storage and Kubernetes. Who's here to hear about storage? Okay, I thought you're at the right place. What I thought would be interesting to do is to actually walk through. I think you hear the term storage and persistent storage, and people think about storage in different ways. So maybe we can start with a review of storage in Kubernetes, and then lead up to where I think we should be going, or we are going with storage. Can everyone hear me okay in the back? Okay. So here's my fancy drawing of a Kubernetes cluster. There's the masters and the 3 nodes. Typically, when when Kubernetes first started, there was no persistent storage. There was nothing outside of a cluster. So this is, I can't remember which version, but essentially, if you wanted to store data that survived a pod moving between nodes, you were kind of screwed. All storage was essentially on the actual node, and that was all that was available. You heard the big announcement today around 1.6 with dynamic provisioning. Where we've gone is that with Kubernetes, you can now manage volumes that essentially are provided by external storage clusters. So if you think about what that means, just like managing the network or managing pods, managing replication and all those things, Kubernetes can now manage the creation of volumes and the mapping or attaching of volumes to pods, right? But Kubernetes does not manage the other side of the volume, the actual storage cluster providing these volumes, right? So if you're in a public cloud environment like AWS or Google Cloud, that's typically not a problem, because you have persistent disks, or you have EBS, or you have your cloud provider's storage that, with dynamic provisioning, Kubernetes can essentially mount an EBS volume, attach it to your instance. It could make it available as part of the pod, and the same with Google Persistent Disk. If you're not running in a public cloud environment, you're kind of out of luck. You essentially have to run a storage cluster that can provide volumes to Kubernetes somehow. And the way you do that is it's an external thing. It's not part of the Kubernetes environment. So if you're running a software-defined stack, such as Ceph or Gluster, you essentially have to run a full deployment of Ceph and Gluster, or Gluster. And you do that in the traditional ways. You do it as part, you typically have storage admins that are managing it. It is essentially a completely external to Kubernetes. Or you use traditional hardware, whether it's NetApp filers or EMC boxes or whatever your enterprise has for storage. You can certainly use those, but it's the same thing. They're completely outside this environment. They require some admin or ticket system or something to provision storage in this world. And it's just essentially external. Making sense so far? I would love an interactive session with you. Feel free to ask questions. I'm happy to make this as interactive as we can. So what if we brought the storage cluster into the Kubernetes environment? Instead of having it be an external beast that's managed, and just like we've done with, say, networking, or like we've done with monitoring, or like we're done with load balancing, what if we actually ran the actual storage cluster and had it be managed by Kubernetes itself? So if we did that, then to create the storage cluster, I just kubectl and I start up a new storage cluster, like I would say a load balancer, or like I would say Prometheus. And what if that storage cluster could actually provide volumes through dynamic provisioning to other pods running in the same cluster. We think that that's what we have to do to solve the storage problem in Kubernetes. We think that that's not only going to be the default way of running storage in Kubernetes, but it's going to unlock scenarios around portability across clouds and the ability to actually reduce the management and reduce the surface area of what is running in Kubernetes. Now, that doesn't mean that you kind of have to run in a converged mode like that. You can actually, if you wanted to, create another Kubernetes cluster just for storage and scale your storage independently from your compute and your applications. But there is no reason, if your organization is settling on using Kubernetes as the single way of managing and running applications, there's no reason why you can't run your storage cluster, even a dedicated one, in the same way that you run your applications. Make sense? So what I thought I would do at this point is just switch over and let's talk about one of these storage systems that now runs in this way. It's a project called Rook. Rook is essentially an open source file, block, and object storage that runs as part of your cloud native environment. It runs as an app in Kubernetes. It's completely integrated. And I'll demo it, and we can walk through all the details of how we're implementing it. Now, before I say that, I think there's going to be a number of these coming up, right? I think I don't know of another one at this point that is running in this way, but I think that trend is a good one. We're going to see more and more storage running in this fashion. And the reason for that is, if you think about software-defined storage, it's itself a distributed application. It's made of many different parts. It needs to be scaled. It needs to be scaled according to certain dimensions, metrics. So it looks like any other application. And Kubernetes is designed to deal with these distributed applications. So it's a really good fit for essentially software-defined storage. So what is Rook? Rook is essentially battle-tested software-defined storage. And I say battle-tested because we based Rook on a version of Ceph, embedded Ceph, that we make part of the Rook binary. Ceph is awesome. Ceph has 10 years of production deployments on top of it, and runs some of the world's largest storage clusters. So what you can think of Rook as taking Ceph and making it cloud native, making it so that it runs really nicely on environments like Kubernetes and integrates it very deeply into Kubernetes. And then we'll see that. Rook itself is open source. It's an Apache 2.0 license. It is, designed so that people like you here, and I'm hoping that you can all help make Rook better, can participate in actually driving storage into Kubernetes. Okay, that's pretty much all the slides I had. Let's actually do some demo and talk. Look at YAML files. I know you're all excited to see more YAML files. All right. Why don't we start with the first YAML file? Can you guys read this? Is this readable? Okay. Yes? I can make it larger. For the guys in the front here, the popcorn section up here.
Sorry, excuse me. Can you move it to the left?
To the left? To the left, to the right? All right. Let's see. Okay. So the first thing we're going to do is that we're going to teach Kubernetes how to manage storage clusters by extending Kubernetes. And the way that you can extend Kubernetes today is by essentially creating an operator or a new controller. So part of what Rook does is it has a controller that's designed to manage storage in a cluster. We've designed this, again, to be so deeply integrated into Kubernetes, and so we're using third-party resources to describe every aspect of the storage cluster, and I'll walk through that. So first, I'm going to create a deployment that starts the Rook Operator. And again, the Rook Operator you can think of as an extension of Kubernetes that helps it deal with storage concepts, pools, storage clusters, file systems, block stores, object stores, etc. And it's a really simple deployment. Right now, just one replica. The Rook Operator is a tiny binary, just runs, and essentially is going to watch for changes in the environment or instructions from the admin about running storage in the cluster. So we'll start with that. And, sorry, it's quite simple. I have a window here that is kind of watching the cluster and showing what pods and resources are in it. And I have a window down here where I'm going to run a command. And so that's pretty much it. The Rook Operator is now running. But the first thing that happens is the Rook Operator creates a set of third-party resources, which is, again, a way to extend the Kubernetes API. The ones we create are for storage cluster, for pools, and a number of others that essentially...
Why age is 22 minutes?
What's that?
Why age is 22 minutes? You just created it.
I don't know. I've been creating and stopping it a few times. Maybe it's the first creation? Good question. There's no magic. This is a live demo. And so once the operator is running, you only have to do this once in a cluster. Once the operator is running, from this point onwards, you can go create new clusters. You can create pools. You can do all sorts of things with clusters, and we'll do that. This is, again, a one-time operation. Now, let's actually look at the YAML for a cluster. So again, this is a fairly simple description. You'll see the kind here is a new kind. It's a Rook cluster. It's not, so a Rook cluster is a third-party resource. By default, Kubernetes does not understand Rook clusters, but we just define them, and I guess we'll... What's that?
Oh, this is good. This is good. Roll back.
Which company do you work for? All right, we'll do this at the end when the demo fails. All right, so now that they have the operator running and all the third-party resources have been declared, we're going to go create a cluster, and we do that by creating a YAML file of kind Rook cluster. So what this says is it's a declarative statement. It says, I would like a new cluster, a new Rook cluster to be deployed on this Kubernetes cluster. And you can also set the namespace that you'd like the cluster to be deployed on, and a bunch of metadata parameters that are essentially define the cluster. Right now, it's very simple. Which version of image to use of Rook. We're just using latest. Whether to use devices or data editors, and a bunch of device filters. You will see a lot more here, but this is essentially the minimal cluster. So I will go ahead and do that. let me just create this cluster. And what happens is an instance of the cluster is created. The operator is watching these third-party resources. It sees that, oh, somebody wants a new cluster, and here are the parameters for the cluster. So the operator wakes up, says, I'm going to go deploy a new cluster. And what the operator does is it actually looks at the size of the cluster, it looks at the number of nodes in the cluster, it looks at storage nodes, it finds, it uses a number of heuristics to figure out what the right size of cluster to deploy. And in this case, and it starts with creating essentially the Ceph monitors, bootstrapping them, creating a quorum, waiting for them to come up, setting their networking, setting everything else around the cluster. And as I said that, this is the time when the screen should come up. There we go. And so you'll see that it created 3 monitors. This is a Ceph term. If you're not familiar with Ceph, Ceph has essentially its own Paxos role where it uses it for essentially maps and consistency in the cluster. So this Rook operator created 3 monitors in a 3-node cluster. It created 3 storage nodes, 1 for each device on each of the nodes, and it set those up. And it created a Rook API server that's also running as part of the cluster. If we were to grow this cluster, the operator will actually notice that the node size has changed, and it will grow the cluster. If we were to shrink the cluster, then the operator will actually also react. It'll reduce the cluster size, it'll move and rebalance the data as needed. Now, a lot of this machinery is done by Ceph, but the Rook operator is essentially what's making Ceph work in a Kubernetes environment, if you want to think about it that way. Question?
Directly talking with Liberator?
So the operator is not on the data path. So the data path is identical to Ceph. That was one of an explicit design point for us. Like I said, it's 10 years of production experience, awesome code base. We did not want to be on the data path. Yep.
Ceph relies a lot on the topology description.
Yep.
The operator, is the operator aware of that?
Yeah, so the other thing that Rook does is it essentially abstracts a lot of the complexities of Ceph around, not that they're not important concepts, but we think that we can expose simpler concepts that essentially ride on top of those. Crush maps, the ones you mentioned, are a good example of that, super powerful constructs. What we're doing is at a TPR level, you can specify a location and topology for storage nodes, and that essentially results in crush maps being created for you and managed for you by Rook. Any other questions? I saw someone.
Another one.
Yeah.
Perhaps you show it, but can you distinguish between SSD, spinning?
Yes. Yep. SSD, NVMe. There's different layouts on each of the storage nodes. Rook is in alpha. So what you're seeing here are alpha bits. I'm sure there's a lot of room for improvement in terms of what kind of layouts and all these things that we're talking about. But so here we go.
Question?
Yes.
Can you describe more how you handle and configure the actual disk that you connect to the node?
Yes.
In the YAML?
Yes. So the basic policy is that in the cluster, you'll see I set the use all devices equals true. This essentially is a flag that says I have a dedicated storage cluster. All physical storage devices will be turned into a Rook cluster, right? So we'll enumerate all your devices, we'll figure out the layout, and we will use them for storage. You can turn that off, and you'd have to tell us which devices on each of the storage nodes, or you could also use just directories, and we'll actually just use a directory. As you can imagine, there's a lot of different policies that people want to specify here, and there's a whole proposal for how to improve that. That's on our GitHub page. Yeah. Question?
The cluster, you said when you increase the size, it will detect and will
Yep.
adjust it itself. And when we shrink it, it will see and it will balance the data you said.
Yes.
So what about if the node fails? What about the lost data with that node? Will it rebuild? Is it some kind of network RAID or something?
Yes. So Ceph is really good at all of that. Ceph has internal mechanisms for detecting when a storage node goes away, but both temporarily and permanently, and triggering essentially the rebalancing and the re-replication of data. So that we take advantage of all of that. At the Rook level, we'll also recognize when a new node shows up in a Kubernetes cluster, and then add it to Ceph and manage that part of it. Yeah.
So if you're taking nodes away from the cluster,
Yeah.
you need to be careful not
You
to
do.
remove all replicas.
Yes.
So is some coordination in doing that?
Not right now. I mean, if you have a storage cluster and you shoot all the nodes in the head, you're shooting your data in the head.
Right. But if you remove two, you could lose
That's right.
replication.
That's right. Right now, there is no, how typically the way that these things are set up is that, they're not on replication is not on a node basis. It's a logical basis. And so removing a node might trigger, some data to move, but it's not a loss, and it's not necessarily affecting a single pool, right? It might be affecting different pools. But if you're asking, if I want to decommission a set of nodes, how do I know which order to do them? There isn't any support for this right now. Yep. Okay, let's move on a little more. So I've created a cluster. At this point, I've deployed a Rook cluster that's running and has an API server and everything else in these pods. It's running in a namespace called Rook. So I have essentially a dedicated namespace for my storage cluster. Let's actually do something with it. So what I'm going to do next, and I'll show you this. This one has a little bit of a hack until we get our volume plugin, but I'll show you. So I'm going to do two things. Now that I have a physical cluster running, I'm going to create a pool. And a pool is essentially a logical construct that says, I want this kind of replication policy, or maybe it's erasure coding, and I can select devices, whether it's SSD, NVMe, etc. And I could use this pool for certain applications or for certain workloads. It maps very closely to the concept of a storage class in Kubernetes. So the approach we're taking is that a storage class can actually reference a pool, but you can create the pool directly from using a third-party resource. So I'm going to do that here. The top part is kind equals rook pool. So that creates a new pool. It's set to replicate, and right now just one replica, it's very, very durable. And on the bottom section shows a storage class, and this is an existing API concept as part of Kubernetes. And there we'll actually point the storage class to the Rook pool. So let's actually do that. So if you're not familiar with storage classes, they're essentially a way for admins to define a policy for how volumes get created, right? From which pools, which disks. In an AWS environment, it could specify the kind of EBS volumes you want to mount. And then once you create a storage class, then people can use the storage class. Application developers can actually use the storage class to create volumes and volume claims. And we'll walk through that. So at this point, I created a pool. I have a storage class. Let's go ahead and go create an application. I'm going to use WordPress. WordPress requires persistent storage itself for its for its content, but it also uses MySQL. And MySQL requires persistent volumes to store the data, to be reliable. So let me show you what that looks like, and then just quickly. So the top part creates a persistent volume claim for the MySQL database that's going to be used by WordPress. And you'll see that there's a storage class set to Rook block, and then a set of labels and size of 20 gigabytes, and the access mode, read-write, right? So this claim essentially matches up to the storage class, and the storage class matches up to the pool, and the pool is connected to the cluster. So that's essentially the chain of how we know which devices end up storing the data that's sitting underneath this pool. And it's also how we know the kind of replication policy, or whether you're using erasure coding, or all that stuff is defined on that path. But it's defined in different forms and different ways, so that there's a nice separation of concern between an admin and an application developer. Lucas?
Yeah, will it be possible to use the read-write many access mode in the future?
I think so, yeah. I think so. It's supported by the volume plugin and by others, yep. Okay, so I will skip the rest. Let me actually maybe just show you the usage of this in case you've not looked at this. So here's the actual MySQL database, the pod for that. You'll see in the bottom here is a volume which uses the claim. So at the time of when the pod is launched or scheduled, Kubernetes will go and it will create a new volume, and it'll do so against the storage class and the pools and everything else. And then when the pod is scheduled on the machine, it's running as, say, about part of Docker, then it will mount, and there's the mount, that volume on that path, right? So let's do that. And you'll see the bottom two lines show that 2 volumes have been created, one for MySQL, the other for WordPress, 20 gigabytes each. Now, after those are created, the WordPress application is running, and so is the MySQL database that's supporting it. All of this was done automatically, right? All the volumes are created, everything in cluster, all of it. Let's actually start it up and see it running. There's WordPress. So let's see. We're going to install WordPress. Log in. And here we go. So a couple of things I want to mention. I only use kubectl to provision this whole thing. I didn't use any third-party tools. I didn't use any other CLI. I truly just used Kubernetes to bootstrap an entire storage cluster and use it itself. Again, a testament to both the extensibility of Kubernetes, but also the fact that you should think of storage as just another app that runs as part of your cluster. Question?
Could you kill MySQL pod and see if it can restart somewhere?
Can somebody press the button again?
Just the MySQL pod.
Kill the pod. I planted him.
No, there's a reason, because I'm working with a PostgreSQL
Yeah.
project right now, trying to make it high available.
Yeah.
And when I kill PostgreSQL, it takes 30 plus seconds on Google Compute Engine to restart another node.
Yes.
So if your project is promising, I'll probably use that one.
You know, it's a very good question, and I'll tell you that some of the early users of Rook do the same thing on AWS, and there the numbers are up to an hour to detach a volume from an instance and attach it to another instance. Could take up to an hour. And so if you're running something like, in this case, Prometheus on top of storage, your beautiful charts look like they have big gaps in them, and you don't know why. And the reason is it's actually just how long it takes to storage. The other reason that people look at this in these environments is that at least in Amazon, an EBS volume is, essentially within one availability zone. You can't say detach it from one zone and attach it in another zone. You have to snapshot and move it, right? By running a software-defined stack, you can actually create a cluster that is across multiple zones. And a pod could fail over across zones without needing to actually do anything in such environments. So again, I was hinting earlier about, whoa, I said Amazon and all these questions came up. Why don't we do that afterwards? I don't even know how to. Yeah. Question. Question. Question.
How attaching volume looks from a container perspective from clients? So who handles its RPT traffic, its file system level?
Yeah. Good question. Right now we're using the standard Ceph RBD plugin. That's part of Kubernetes. That big statement here with all these exports and magic hacks in it is to work around a set of issues with the RBD plugin. We're creating a Rook plugin. We hope it'll be part of 1.7, Kubernetes 1.7, that makes this whole experience a lot better. The other thing I'll say is that Rook is not just like Ceph. It's not just block storage. So you can actually run a shared file system here as well. And so you could go through a path of not just RBD, but CephFS is the other path. And there, you just use whatever your favorite S3 client is, or Swift client.
Also provide the source run gateway?
That's right. Yeah, you could. The way it would look going forward is that there'll be a TPR for object storage. You create a TPR, and then Rook will manage the object store and essentially your own S3 running in the cluster. Yep. Other question?
How do you separate storage traffic from application traffic? As you
Network traffic?
Separates network really huge.
Very, very good question. So, in general, I'll say at the managing resources, Kubernetes has a lot of facilities for managing memory and CPU, and with labels and selectors and all policies you can set. Network traffic, very different story. Typically with CNI, you have one interface that you set on a volume or on a container, and that's all you get. You can play games with things like SRV-IO and others at the host level to do this. You can play games with VLAN coloring, essentially. You can mount multiple networks in a container, even with CNI. There are ways to do that. Right now, we're taking the simple case. It is not the fastest case. The fastest case will be one where you have to color the traffic and prioritize it in one of the ways I just mentioned. Yeah. Question?
Is this like general purpose enough that you could have a setup where you would have like a Kubernetes cluster that's just running this, and then other clusters?
Yes. Yep. That was one of the pictures I showed earlier. Yep. that's pretty much it. I was going to show one more slide and then wrap up. I'm happy to take any more questions. So let me talk a little.
Is the example you gave on GitHub already?
I have it on a gist. We have a bunch of stuff on the README that helps you walk through all of this. I'll put this exact demo on there as well. So just to wrap up kind of what the storage operator is and what it's doing. Essentially, it's defining desired state. This is what I want to happen in my cluster through third-party resources. And you can do those extensions to Kubernetes, just like there's a deployment and a service and all those concepts that are in Kubernetes. We now added a cluster, a storage cluster, and a pool, and object storage. And all those are essentially concepts that are now extending Kubernetes. The operator tries to achieve this desired state, the will of the admin, the desired, by watching both what's happening in the network, what's happening in the cluster, and watching the actual desired state. And it's sitting essentially in a loop, just like other controllers, trying to make actual state approximate desired state. That's the role. And it knows a lot about the storage cluster itself, so it's doing it in a way that is very, understanding of the fact that this is stateful data and needs rebalancing and nodes come out and all that stuff. And then the last part I'll say is that it's not on a data path, can be offline for minutes. Not everything will run, but when it comes back up, everything's normal. And it can run in an HA pair through a deployment if we need it to. And finally, if you want more info, go there. Lucas here is doing a talk tomorrow that has showing kubeatom and Rook on Raspberry Pi. Do not miss that talk. It should be really cool. It's tomorrow at 1400.
Very good.
Yep.